All right, welcome to lecture 17. So in this one, we're going to talk about three different topics. Part A, that's the part you're watching right now. We're going to learn about what something's called a ionic and a net ionic equation. So that'll still have to do with precipitation reactions, which you heard about in the last set of videos. So we'll be talking about those again a bit. Then we're going to move on to our last type of reaction we're going to cover, which are called acid-base reactions, and look at those as well. And then finally, in the last part, part C, we're going to move on and talk about calculating how much stuff do you get in a chemical reaction. So not just looking at a reaction, trying to figure out how much you actually make. I notice there's a little typo here. This should be 17, right? 17A and B, B and C. All right, let's go and get started today. All right, so again, for ionic and net ionic equations, that's a new topic. But before we do that, we actually need to kind of talk about precipitation reactions just a bit more. So precipitation reactions, remember those are the ones where you figure out the product, and the product is going to be some sort of solid. And the way we know which solid is we have these solubility rules, all right? So again, it's going to be a little hard to show you these rules. If you have a way of printing them out, they're posted on Canvas. You could look at them there. So keeping these handy for this part of the lecture would be a good idea. All right, let's get to an example. Let's get to an example, another one involving precipitation reactions. All right, so we have another reaction here we're going to finish right now. I need to do one more similar to what you saw in the last video because our new topics kind of relate to this. So we need to kind of go back and do one more example of writing out a precipitation reaction. So we're going to mix these two things together, and I could look at the solubility rules to prove it to you. But both of these are compounds that dissolve in water. They're both aqueous. And when we mix them together, we're going to try to figure out what we make. All right, so this is the one, the kind of reaction, remember, where you have to, what was the first step? Determine your charges. And then after you determine your charges, you do switcheroo. The positive of the first goes with the negative of the second, and the negative of the second goes with the positive of the first. All right, and then after you determine, you do your switcheroo, that's the one, then you determine formulas based on the charges, the formulas of the products. And then from there, we're going to balance the reaction. And then finally, the last step is there should be a solid, so we'll ID the solid. All right, so let's go ahead and get into it. So I'm going to see if you can help me with this one a little bit. So let me kind of get you started, and then I'm going to give you a few questions along the way to make sure this is sort of making sense, I hope. All right, so step one, let's determine our charges. All right, so I'm going to start at the end of the line here. Chloride, right here, find on the PR table, -1. All right, so he's got a -1 charge. And then we'll move over to magnesium. Magnesium is right here. What's the charge on magnesium when it's part of a compound? Oh, +2. Let's keep on going down the line. We get to NO3. NO3 is called nitrate, and I'll put it right here. It's a polyatomic. You can find it on your handout. It's -1. All right, that's called nitrate. So nitrate is -1. And then we get to Ag. Now, Ag is a weird one. It is an always and forever. Do you remember that one? Silver right here. He was sort of a straggler fella. He's +1. He does always have a +1 charge. All right. So in this reaction, it looks like we're mixing AgNO3. That would be silver nitrate. We're mixing it with magnesium chloride, MgCl2. All right, so step one, we're done. Determine your charges. Step two, switcheroo. Hey, hey, boo-boo. I'm like Yogi Bear. I love Yogi Bear. All right, so now what we're going to do, what that means is you put the positive of the first with the negative of the second. Mr. Silver is getting together with Ms. Chloride. When you bring them over, what do you bring over? You bring over the charges or the subscripts? You bring over the charges, not the subscripts. So silver is still +1, chloride is -1. the same ones we found on the periodic table. Those stay the same. What you wouldn't bring over is a subscript, like that 2 right there, right? That 2 does not go over. Subscripts don't travel, charges travel. All right. Now with that, let's move on to the next one, the second product. So the other product is my middle fellas getting together. Now, I got to do a couple things. Let me remind you, middle fellas, flippity floppy them. Why? Because you always list the positive thing first. So Mr. Magnesium is getting together with Ms. Nitrate. So it's going to be something like Mg will be the first thing in the formula. Why? Because it's positive, and then the nitrate's negative. So it's always plus and then minus, right? In a formula. Other thing, why? I got a lot of why questions right now. Why? Why does the 3 stay here? It's because it's part of the polyatomic. So subscripts that are on the polyatomic list, bring them over for me, all right? But not any other subscripts. Charges go, subscripts from the polyatomic list goes, nothing else goes. All right, so now we're ready to write our formulas. Now, hey, here's where you can get a little practice in. Practice is going to make you a better chemistry student. All right, so question 1. Silver and chloride are my first product. What's the formula? Should be AgCl. All right. Second one. What's the formula for my next product? Magnesium and nitrate. What's the formula when they get together? Hey, only thing I want to warn you about in this pop-up question you're about to get, I can't really do subscripts. So like the numbers, pretend they're subscripts, okay? All right. The formula for the other product should have been MgNO3 2. All right, should look like that. Oh, does that make sense? I hope it does. All right, so with that, now we've already done the first 3 steps. Oh, wrong color. Wah, there we go. Check that one off. All right, so it's getting a little bit messy. Let me rewrite it real quick, and let's see where we're at. So far, we've got this AgNO3, which is a liquid, aqueous thing, reacts with MgCl2, which is also aqueous, and it turns into AgCl plus MgNO3 2. Oh, got a little messy there. Sorry. Okay, so next step, balance the reaction. So balancing it means that you got to get the same number of atoms on both sides. In the interest of saving us a little time, let me just kind of show you how that's going to go. All right. If I go through it a little fast, you could always rewatch it, right? All right. So let's make our list. I'm going to just do it in my head. What's a good color? A silver. Seems okay. A nitrate, 2 nitrates. Problem. We need the same amount of nitrates. We're going to put a 2 here. All right. So that gives me my 2 nitrates. Just like I have 2 nitrates over here. All right, so nitrate is balanced. But you know what? When I put that 2 in there, it also changed my silver, didn't it? So there are 2 silvers on the left. So I need to get 2 on the right. So the way to get 2 on the right, we're going to stick some right there. We're going to stick a 2 right here. All right. Oh my God, that's a little messy. But there's a 2 there. All right, and then let's see where we're at. Silver seems balanced. Nitrate's balanced. Magnesium, 1 magnesium. 1 magnesium. Magnesium seems okay. And then finally, 2 chlorides. 2, because that multiplies, 2 chlorides. So let me erase this. I think it's balanced. We needed a 2 in front of the AgNO3, and then we needed a 2 on the right-hand side in front of the AgCl. All right, last thing we got to do. Somebody is the solid. Now, unfortunately, I cannot show you those solubility rules. Let me just tell you what they say. All right, the solubility rules say anybody with nitrate dissolves in water. You got nitrate in you, you dissolve in water. Nitrate is NO3. So the last fella, since he dissolves in water, we write AQ. Hey, you dissolve in water. All right. Now there's another rule. It says chloride. Things with chloride typically dissolve in water, But if you check out the right-hand side of that handout, there's an exception. Things with chloride typically dissolve in water, but not if they have silver. So silver chloride actually doesn't. So we write an S. You don't dissolve in water. All right, so this is what we're going to make. So we mix these two beakers together. Now these two things, you pour one into the other. When you pour them together, you're going to get a solid at the bottom. That solid would be AgCl. And then above it, there would be like magnesium and nitrate ions, okay? So we form a solid. So we would start off with two solutions, and we make a solid. All right, so with that, that's kind of what we did last time, right? It's a little confusing, so you got to practice it, mainly because I think the reason why it's a little confusing, right, is you got to know your charges, you got to know how to write formulas, all that stuff. There's a lot to keep track of. So the other thing we're going to do with this example, though, is we're going to learn that what I've taught you so far is only one way of writing out a reaction. When you write out a reaction this way, where the way you've been used to doing it, I didn't tell you the name of it, but this is called writing a molecular equation, a molecular equation. Now, there are other ways to represent the same experiment, the same process. So let's talk about what those ways are, and then we're going to take the same reaction and we're going to write it just a little bit differently. All right, so what are the other ways first? The other ways are, first off, called an ionic equation. An ionic equation shows a reaction in water a bit more realistically. Why is it going to be a more realistic way? Because aqueous substances are shown as being broken up. And that is actually more realistic. A week ago, I told you, when you have something and it dissolves in water, it actually splits apart, like salt, for example. Those ions are actually separated by the water, all right? So we're going to show in an ionic equation things that break up. We're going to list them as being broken up. Now, if you're a solid, liquid, or a gas, we're going to leave those together because solids actually are when ions are still stuck to each other. The same thing is true for liquids and gases. We won't get into that too much in this lecture, though. All right, now there's one other way to write an equation. So a net ionic equation, we'll do an example in a minute. Anything that are aqueous, you break up. Last way to write an equation is called the net ionic equation. And in a net ionic equation, it only shows substances that are changing, and you cancel out items that are the same on both sides. You cancel out items that are the same on both sides. All right, so two other ways to show the same reaction happening. Let's get to it. And to do an example, I'm going to actually take the reaction we just wrote out. And the easiest way to get an ionic equation or a net ionic equation is to have that molecular equation, the one we just came up with, and then think of kind of converting it to these other forms of writing out reactions. So let's do that. So let's go back to the reaction we just saw, and let's take it and turn it into an ionic equation, and then finally a net ionic equation. Okay, let me rewrite that equation we just came up with real quick. So the way that you're used to writing equations so far are called molecular equations. And the example we just did and came up with was this, right? AgNO3, it's aqueous, reacts with magnesium chloride, which is also aqueous, turns into 2AgCl, which was a solid, that was the precipitate, and then we also get MgNO3, 2, which is also aqueous. All right, so anything that is aqueous, I'm going to split apart. Now, there's lots of little tricky things that can mess you up. All right, first off, anything that's aqueous, I'm going to show separated. Why on earth would I do that? Because when things are aqueous, water has actually broken up the pieces. So I would, for example, AgNO3 is aqueous. So I'm going to split it up into the two ions. It's kind of like the same ions that we put together when we write a formula, right? Now, there's some important details about that, though. Detail number one, any fella you break up, you put the charge next to. Silver is +1, nitrate is -1. You have to show the charges on anything you break up. All right. Second important detail. We have to keep track of the amounts. So this 2 that we put in a minute ago to balance the reaction, that would still apply to both things in that formula. 2 silvers and 2 nitrates. So when it breaks up, I get 2 silvers and 2 nitrates. Now, the next fella is also broken up. All right. So we're going to, it's aqueous, I should say. So we're going to break it up. Yeah. So magnesium is going to split from the chloride. Now, a couple other important details. Anything you break up, you have to write the charge on each ion. Now, again, can't really go back to the periodic table too well on this little tiny screen, but, you know, we talked about it a minute ago. Magnesium has a +2 charge. Chloride has a -1 charge. We write out the charges on our broken up things. We also keep track of the amounts. Now, this kind of goes back, what I'm about to tell you, to something I showed you a while ago when I talked about how things break up in water. Do you remember how I told you, and I kind of ripped up a piece of paper, that when something that's ionic breaks up, oh, where's my camera? Right there. The magnesium is going to fly off and swim on around the water. He's going for a swim in the water, the magnesium, all right? And the chlorides also break up and swim around the water independently. So you get 2 chloride pieces. When we talked about this last week, I said the way that you show me that is you actually make that a coefficient of 2. So let me tell you what I don't want you to do because it's wrong. I don't want you to do it wrong, right? If you make it a subscript to 2, that is incorrect. If you leave it as a subscript. Because subscripts have to do with things connected. So if they break apart, they are no longer connected. So it needs to be a coefficient. All right, it needs to be a coefficient. All right, so let's do the right-hand side now. Oop, I got to change my pen. On the right-hand side, we break up things that are aqueous. AgCl is a solid. Leave it alone. Leave it together. So when things are a solid, why are they a solid? It's because the positive and negatives, the silver and the chloride, have stuck to each other. And when you stick to each other, in this case, that material is a solid. So they are still bound to each other. So we're going to show them connected still. Now, the last product is aqueous. Split it up. Magnesium and nitrate. Now, the only other thing I would do is I would show the charges. 2 and nitrate's -1. Now, there's still one thing I'm missing. Do you have a guess? What am I missing in there? Oh, this 2 tells me when it breaks up, I actually will get 2 nitrates. It should look like that. All right, yeah, there's a lot to do. This is kind of a little painful, isn't it? All right. So anything that's aqueous, you break apart. Charges get written out for broken up things, and keep track of your amounts. Now, the last thing I'm going to tell you is all these things, when they broke up, they're still aqueous. So you really should write little AQs after them. So yeah, there'll be some sapling homework on this. And they might ask you to write all those AQs in. All right, on anything you broke apart. That's called an ionic equation. Oh, I should have left a little more room here. We just did the ionic equation. Oh, I don't want to write that there. That's going to mess me up. All right, maybe I can fit it in right here, I hope. This is called an ionic equation, what I just did. Okay. Now, there's still one more version of an equation. And the last version is called a net ionic equation. Now, in a net ionic equation, anything that is identical on both sides of the arrow cancels out. All right. Mr. Nitrate, he was an ion. He was dissolved in water. When the reaction is over, he's still an ion dissolved in water. I'm going to cancel him out. Magnesium was an ion. When the reaction is over, he's still an ion dissolved in water. I'm going to cancel him out. So in a net ionic equation, you only tell me things that actually changed. So there were some silver ions. They were swimming around in water. They bumped into chloride ions. They were swimming around in the water. They turned into a solid when they met. That's the net ionic equation. All right, now if you're wondering, yeah, you could actually, do you see how the coefficients are divisible by 2? You could even divide it by 2, and if you want, you could write it this way. Mr. Silver ion reacted with chloride ions to turn into silver chloride solid. Okay, that would also work. All right, yeah, man, there's a lot to keep track of, isn't there? That's why we're going to practice this. So I should tell you, if you're in the lab, you're going to practice this in lab. If you're coming to my Zoom sessions, I hope you are, you're going to practice in the Zoom sessions because, man, it's, it takes a little while to get the use of. Now, I am going to show you one more example in this video. And again, after I do one, I want you to be able to help me out a little bit. So in the next one that we're about to do, I'm going to give you a chance to kind of give me a little help on some of these. We'll do a few questions here. All right, so let me move on to another slide and we'll do one more. All right. All right, one last example of this. One last example. Okay, so we're going to mix, I guess the first thing there would be potassium phosphate. Again, I really have a hard time showing you those solubility rules at the same time. If you check it, I promise this thing is aqueous. And we're going to mix it with nickel, I guess this would be what? Nickel 2 chloride. Nickel 2 chloride. All right. Tell me what you make. Show it to me. So we're going to write out all 3 versions of this equation. We'll first start off with the molecular one. That's where you got to go through those 5 steps. What were they again? Step 1, determine your charges. Let's do it. Potassium, right here. What's its charge? +1. Phosphate, this polyatomic. It's on the polyatomic list. Check it out if you don't believe me. -3. That's called phosphate. All right. Then we get to the next compound. So actually, I think we're going to have to start with chloride there, won't we? Chloride is -1. And then I need to know the charge on nickel. Now, I think I said it a minute ago, but just to make sure you know why. 2 chlorides, each one is -1. Nickel can have more than one possible charge. It's not an always and forever. So the nickel has to be +2 in this reaction, all right, in this compound. So if there's 2 chlorides and each one's -1, the nickel has to be +2. Okay, we know all our charges. All right, you know your charges. Oh, but let me erase this. I don't want it to be too ugly here. All right, so after you know your charges, step 2. Switcheroo. All right. Outers get together, middles get together. When you put the outers together, I am talking about, maybe I'll put it in red, the K and the Cl. +1, -1. I should write that in, huh, maybe. All right. Don't bring over the subscripts. Do not bring over the subscripts, people. Do not bring over the subscripts. Okay. Now, we're going to do the next one. We'll put the middle guys together. Nickel with phosphate. All right, now we got to know the formulas. All right, first set, K and Cl. Oh my God, that's not too bad, right? +1, -1. Do you want me to write any more subscripts on there? I don't think so, right? It's just going to be KCl. Now, what's the formula for the second one? Nickel and phosphate. I'm going to let you think about this one. Nickel and phosphate, the second thing we make. What's the formula? Oh, I hope you know. It is Ni, should be Ni3, PO4, 2. How did I know that? Well, again, you got to balance out your charges, right? Another phosphate, please. 6 negatives. And then you need 2 more nickels, right, to get 6 positives. So yeah, that's the right formula. Ni3PO42. Okay, with that, we already done the first 3 steps. All right, now it gets a little messy. Give me just a minute, please. I'm going to rewrite where we're at. This is what we got so far. That's a Q. All Now, next thing we're going to do is we're going to balance this thing. All right. So again, I'm going to let you help me with that a little bit. So balance, got to get me the same number of atoms on both sides. All right. So to balance it, I'm going to give you a hint. I'm going to give you a couple of hints. Potassium. Let's do a little bit together maybe, huh? There are 3 on the left. So right now, it looks like I would need to put a 3 here to get 3 on the right. Okay. Now potassium's balanced. Now let's move on down the line. Phosphate. 1 on the left, 2 on the right. So to fix phosphate, what number do you want me to put there to fix phosphate? A 2. All right. So you need to put a 2 right there. Now, this happens, and I got some questions already about this. People get confused by this. So when I put the 2 there, I needed it to get the PO4 to match up, right? 2, and because there's 2 over here. But what did that also change? That also changed my potassiums. So how many potassiums are on the left now? There's actually 3 times 2. There's actually 6. So you know this 3 we put in here a minute ago? We're going to have to adjust it. Just because you write a number down doesn't mean you can't change it again. You do need to change it. So I needed, so far where I'm at right now, there's 6 potassiums on the left. So what number do I put here to get 6 on the right? 6 Ks. I hope you know you need to put a 6. 6, right? So the way to get 6 on the right is you put a 6 there. Now, let's see where we're at. 6 potassiums. 2 times 3 is 6, just like over here there's 6. I'm going to erase some of this. Potassium is good. Give me a minute. Okay. Phosphate. Phosphate. 2 phosphates. 2 phosphates. Good. All right. Let's keep on going down the list because I don't think we're quite done yet. So then we got to balance the next thing. The next element I see is nickel. Nickel has, let's see, right now there's 1 on the left. There are 3 on the right. So to balance nickel, we're going to put a 3 right here. And then that balances nickel, 3 and 3. Yeah, we're balanced for nickel. And then let's check the chloride. We haven't checked the chloride yet. Chlorides, let me erase this. For the chlorides, there are 6 chlorides. And what do you know? We have 6 on the right. So that is balanced now. All right, so the coefficient should be 2, 3, 6. All right, with that, let's keep on going. Last step, tell me who the solid is. Oh, man, I can't really show you these rules. So I hope you find the rules, and I want you to right now tell me which one is the solid. Is it the first compound, the KCl? Is this the solid? Or is it the Ni3PO4? Which one's the solid? Look at the rules. Oh, it should be the second one. There's a rule that says anybody with chloride, you dissolve in water. Looking at the solubility rules, anybody with chloride, you dissolve in water. So we're going to write AQ here. There are some exceptions. This is not one of them. There's also a rule for potassium that tells you if you got potassium in you, you dissolve in water. And then there's a rule towards the bottom that says things with phosphate typically don't dissolve in water. So if you don't dissolve in water, what does that mean? It means you're the solid. All right. So with that, this is our reaction. Okay. All right. And again, I want to try to erase this because I'm trying not to make it too messy. There you go. Maybe that makes it a little cleaner, huh? All right. So what did we just write? What's that called again? Molecular equation. So now we're going to take it and turn it into an ionic and a net ionic. Let's do it. Ionic equations. What did I say about an ionic equation? What kind of things do you break apart? Aqueous things. All right. So anything that's aqueous, we're going to split up. Okay. So let's go ahead and do it. Split me up. All right. First fella, split them up. K from the PO4. Those are the 2 ions. You break them up. What do you have to do? Write the charges on them. What do you have to do? Keep track of the amounts. Now, I want to be careful with this. How many potassiums are there? Because think about that 2, right? Think about this 2 and think about this 3. How many potassiums are there really over here? There's really 6. So you should have a 6 in front of the potassium. It's kind of like when we're balancing and I say, how many potassiums are on the left-hand side? Whatever you tell me, that's your coefficient. All right, how about for the phosphate? How many phosphates are on the left-hand side? There's 2. So whatever you tell me, that should be your coefficient. 2 right there. All right, let's keep on going. Now we're going to keep going on the line. If you are aqueous, I am splitting you up, man. All right, next compound is aqueous, so we split it up. Nickel and chloride. Tell me the charges. The same charges we figured out earlier. +2, and we could look at the periodic table, or we even wrote it here, -1. All right.
I don't know that one.
Alexa, what are you talking to me about? Did you hear my computer speaker was talking to me? She doesn't know this. That's okay. You're going to learn it. All right. So, all right. After you write out the charges, what else do? You keep track of the amounts. Nickels. 3 nickels. All right. And how many chlorides? 3 and 2 there. There's actually a total of 6. You got to multiply. It's just like when we're balancing. I said, how many chlorides on the left-hand side? You told me 6. That's your coefficient. Oh, and a little messy. Let's try to make it a little cleaner. All right. Should be +6 right here. And again, let's try to make it a little better. Let's be consistent with our colors. There we go. All right, right-hand side. We're going to break up things that are aqueous. K and Cl. We're going to write out the charges. +1, -1. You can glance at your periodic table to remind you of those if you forget them. Keep track of the amounts. Now, just like when I balanced it, if I was to say how many potassiums are on the left-hand side, or the right-hand side, I suppose, well, you got that coefficient, right? So there's 6. And that 6, if I said how many chlorides are on the right-hand side, you would tell me there's 6, right? Because the 6 really goes with both of them. So this 6, there's 6 potassiums and 6 chlorides. Now, the final thing is a solid. You ain't going to break him up. You would not break up gases or liquids either. Again, that won't come up in this lecture, but maybe it will in lab, actually. All right, so that, and maybe in the Zoom session, if we get to it. Okay, all right, so that is the reaction. All right, now, last thing, cancel out anybody who doesn't change. When you cancel out things that don't change, that's called the net ionic equation. So things that are aqueous on both sides cancel out. All right, do you see anybody who cancels? You should see 2 things that cancel. What cancels out? It should be the Mr. Potassium. He is an ion. He is an ion. Bye-bye. They're also an ion and an ion. Chloride cancels out. So the net ionic, you just tell me about who actually went into creating this solid. So the phosphate bumped into the nickel, which turned into nickel phosphate solid. All right. So that's called the net ionic equation. Man, is this complicated? Yeah, it's complicated. Do you need to maybe watch this again? Wouldn't hurt, would it? All right, so you can always watch it again and watch me do it again. And again, we'll do some in our Zoom times too, because this is definitely, you got to practice this. All right, so with that, one last thing I want to tell you, because I don't want you to get mixed up. And I'm going to have to check on sapling, and I'll let you know in our Zoom sessions. You might, anything that's aqueous, you might need to write AQ in here for sapling to be happy with you. I really don't remember off the top of my head. It's not a bad idea, all right? Anything you broke up, maybe write a little AQ after. The last thing I have to tell you, and again, I'm not sure how particular sapling is going to be about this. Do you see that net ionic equation? The way I wrote it, to me, I don't see any issues with it, all right? You could write it that way. But sometimes some teachers, and potentially sapling, if it causes you grief, sometimes people want you to always write like the positive ion in the beginning of the equation. So to like flip it and to show me the positive fella first. I don't know if it's a big deal, honestly, to me, because you can usually list them either way. But if sapling is telling you an answer is wrong, maybe just to be safe, write the positive guy first in the net ionic equation. All right, the green answer, maybe it's slightly better. I don't know if it really matters too much, though. All right, with that, that's it for this one. All right, man, we got a lot to cover. So there's 2 more parts to this lecture. So again, take a deep breath, go get a drink, and we'll move on to part B when you're ready. All right. So if you have any questions or concerns, I'm absolutely happy to help you with this. This is definitely can be a little challenging.